Okay, folks, sorry about missing class today. It was just sort of a very odd morning. In fact, I'm still kind of dizzy, so if you hear a big ka-thunk and wonder what in the hell that was me falling over to the side. So, what we're going to talk about today is methods of polymerization. Now, what we're not going to talk about is mechanisms. Mechanisms, I mean radicals, cations, anions, or catalysts. With methods, I call this where the rubber hits the road. We're talking about literally what and how we mix to make high polymer. Now, high polymer is a phrase you may not have heard before. What that means is high molecular weight. And what does high molecular weight mean? Because you'll notice I'm not giving you any hard and fast numbers here. What high molecular weight means is sufficient for desired properties. D-E-S-I-R-E-D. Desired properties. There are four principal modes of polymerization. Four principal methods. We're going to talk about them all in turn. Bulk, solvent. The third one is suspension. And the fourth one is emulsion. All right? Now, let's just go through these in order. Bulk polymerization. In this reaction, the monomer, all you've got is monomer and initiator. That's it. So your solvent is the monomer. Now, if this were the military, for the initiator fragment, I'm going to do radical, although it is possible to do cationic or anionic with this. The radical has a target rich environment, meaning there is lots and lots for that monomer, for that initiator to react with. Now, there are a few advantages to bulk polymerization. Those include, one, the setup is simple. Folks, it's really easy. You pour, you heat it up, you're done. At the end, you are going to get really pure polymer. Your molecular weight distribution can be tailored. All right, disadvantages. And this is considerable. Bulk polymerization is not the best for doing a lot of polymerizations. You have massive heat transfer. Issues. Remember the Tromsdorf effect? Or thermal runaway? Very commonly seen in bulk polymerizations. 2, another big issue is you tend to get very high molecular weight. That doesn't seem like it would be a disadvantage, but trust me, when it comes to processing, too high a molecular weight can be very, very choresome. And finally, number 3 here, high chance of monomer boiling out. You can lose a lot of monomer by just the general amount of heat that goes into these things, and therefore lower your molecular weight. So this is commonly done in a few examples, although it's really being phased out. Now, probably the next common one to it would be solution polymerization. Now, in a solution polymerization, as you can probably guess from the title, we've got monomer, our initiator, and our solvent. All in that batch. There's one more thing that has to happen for this to work. The polymer must be soluble in the solvent. More on that in just a minute. Because there's some really sexy things you can do with this. So, advantages here, particularly when compared to bulk polymerization. The biggest issue with bulk polymerization, honestly, folks, is the heat generated. For a solution polymerization, before we dive into it, let's talk about the role of solvent in any reaction. There are several roles a solvent can play. The big two are, 1, common phase for the reaction. The common phase for the reaction to occur in. If you have two molecules that aren't interested in interacting, you're not going to get any reaction at all. Think of the solvent, so think of that, the two molecules not wanting to react with each other. Think of that like boys and girls at a middle school dance. Boys on one side, girls on the other side, nervously looking at each other, not sure what to do. The solvent in this situation is the spiked punch bowl in the middle. A little bit of a spiked punch bowl. People tend to loosen up a little bit. It gets a little more fun. Boys start dancing with girls. And you're asking yourself, what kind of middle school did he go to? Middle of the country, folks, and there wasn't a damn other thing to do. All right, so common phase for the reaction, that's the one that is the most commonly understood. The second that people tend to forget about is the solvent serves as a heat sink. Remember, all polymerization reactions are exothermic. This is what causes thermal runaway or the Tromsdorf effect in some free radical polymerizations. Well, in these situations, the polymerization reactions all being exothermic, now that heat generated has some place to go, and it goes off into the solvent, and the heat is dispersed, meaning you don't have the issue of thermal runaway with it. Now, this is the big advantage of having a solvent, is you've got place for that heat to go. Another advantage is in solvent polymerizations, they tend to have lower viscosity. They tend to have lower viscosities, so they're easier to work with. Okay, problem at the end of this. I'm going to switch to the next page here. Solution, polymerization, continued. The problem with this at the back end is you've got to get rid of your solvent. In order to be able to appropriately process the polymer that you're working with, you've got to be able to get rid of that solvent. That can be very, very difficult, because if your instinct you're thinking is, well, just boil it off. Not a bad idea. That's what we typically do with unwanted solvent. The problem is the polymer chains, especially if that solvent gets captured in some of the void or there's a good solvent-polymer interaction, the polymer chains are not going to want to let that solvent molecule go. Now, I promised you something I said was really slick, and it's so slick, I'm going to switch colors of pen. There are some solvents that will solubilize the polymer only to a set molecular weight. Think about that for a second. Your solvent will dissolve the polymer, but only to a set molecular weight. That means you get to, once you reach that target molecular weight, the polymer precipitates out of solution. What does this mean? Very narrow polydispersity. All the chains are about the same size, which is really kind of clever. All right, I am running out of time for this video. So really quick, I'm going to say tune in next time, or for the video I'm going to record in just a minute, tune in next time for the suspension polymerization, and then we're going to test the limit knowledge I have of emulsion polymerizations. Stay cool, everybody.